All right. Welcome. So now we're moving on to chapter two. Chapter two, we're going to discuss some basic biochemistry, so biochemistry at a very basic level. Okay, so let's talk about chemistry of life. So biochemistry, like the chemistry of life from a biological point of view. Okay, and we'll try to limit it to just the basics. Okay. So matter is any material that takes up space. Um, okay, so matter can be broken down into smaller things until you get to elements. An element is a substance. Elements like oxygen, hydrogen, carbon cannot be broken down into other chemicals. Okay. Okay. So I'm sure you guys have all seen this at some point in high school. This is a periodic table. The periodic table lists all the known elements. Okay. The four that you definitely have to know, the four major elements that make up life: hydrogen, carbon, nitrogen, oxygen. These four make up about 96% of all the atoms that are in your body. Okay. Each box in the periodic table lists the atomic number, the element, the symbol, and the atomic weight. Okay. All right. So let's skip forward. Okay. Atoms make up all matter. This is an atom. An atom is the smallest piece of the element that contains the characteristics of that element. Okay. An atom is made of three subatomic particles: protons, neutrons, and electrons. Okay. Electrons surround, so let's talk about electrons first, because most of chemistry has to do with electrons. Okay. Electrons surround the atomic nucleus. They are very, 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 very small and move very, 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 very fast. They move almost at the speed of light. Okay. So these are electrons. They go around the nucleus. Okay. The protons and neutrons are so close together in the atomic nucleus, which is the center of the atom. Okay. Protons have a positive charge. Electrons have a negative charge. Neutrons, by definition, are neutral and they have no charge. Okay. In terms of mass, protons and electrons have a mass of one AMU, atomic mass unit. So they took atoms and kind of weighed them and kind of divided them in units. Protons and neutrons have a mass of one. Okay, technically neutrons are slightly heavier than protons, but you don't need to know that. Okay, electrons are about 1/2000th of a proton, so they're really, really small. So effectively, they have a mass of zero. Okay, they do a lot of things. They move very quickly, so they play a huge role in electricity, obviously. So they have a negative charge and they move around the nucleus. Protons and neutrons are actually kept within the nucleus. Okay. All right. An ion is by definition a charged atom. Ions are formed when an atom either gains or loses electrons. Okay. The hydrogen ion is positively charged because it's lost an electron. So an ion is a charged atom. So you can either gain an electron or lose an electron. If you gain an electron, you gain a negative charge. You gain a negative charge, you become negative. Okay, you lose an electron, you lose the negative charge. And you do so, you now have more positive charges than negative charges, so you become positive. Okay. Okay. Protons determine something called the atomic number. So the atomic number is the number of protons that are in that element. Okay. All right. Okay, the atomic mass. So the atomic mass is technically all the mass of the whole atom. Remember, electrons effectively have no mass. So the atomic mass is basically the number of carbons, sorry, the number of protons plus neutrons. I'm looking at a carbon atom, like I said, carbon. So the carbon atom, the carbon atom usually has 6 protons and 6 neutrons. So 6 plus 6 is 12. So the atomic mass of carbon is about 12. Okay. An isotope is different forms of the same element. So remember, element has to have the same number of protons. It does not have to have the same number of neutrons. Okay, so you can change the number of neutrons. Okay, so here you have carbon 12. This is carbon 12. You have 6 protons and 6 neutrons. Okay, that's usually the case, but occasionally there are C13, which there are 7 neutrons instead of 6, and even rare, there are C14, which they have 8 neutrons instead of 6. Okay. So isotopes have the same atomic number, but different atomic mass. Okay. The atomic weight, when you look at a periodic table, it's never like a nice even number. And the reason why it's never a nice even number is because every element has different isotopes and they never average out perfectly. So oxygen, for example, usually has 8 protons and 8 neutrons, but occasionally there is 1 less neutron. So it's 59.994. Okay. So recording. All right. Okay. So next concept, chemical bonds link atoms together. Okay. So atoms are organized into molecules, 2 or more chemically joined atoms. Okay. So the most common molecule that most people understand and see is water, and this is water. Okay, water consists of the formula for water is H2O, which means there's 2 hydrogens and 1 oxygen. So formula for water, H2O. So compounds are actually molecules of 2 or more elements. Okay, so how you determine chemical bonding are something like electrons. So electrons are in the outermost shell. So if let me explain how far away everything is in terms of what you can visualize. Like if you or humans, if atoms were human size and you were the nucleus, the electrons would be somewhere near San Francisco. Okay, like there's not much room really between the electrons and the nucleus. And so what we think of as chemistry, the chemical bonding, is always going to be with the electrons. The electrons determine chemical bonding and determine how they interact. Okay. Okay. Electrons exist in energy shells or orbitals. Okay. So you fill in the electrons in the lowest energy shell, and then the largest energy cell, the energy cell on the outside is going to be responsible for bonding. Okay. The way this works is there's 2 electrons. Okay. Actually, let me just type. There is 2 electrons for the first shell, and then 8 electrons for every other shell. So also known as the octet. Okay, so for example, okay, there's 2 electrons in the first shell here. There's hydrogen, there's only 1, so there's 1 bond that needs to be formed. There should be 8 around carbon, so there's 1, 2, 3, 4. So there's only 4 there, so there's 4 bonds that need to be formed. If I look at oxygen, it should be 8, and therefore there's missing 2, so 2 bonds need to be formed, etc. Okay. Well, next one. Okay, so when you bond with other atoms. Okay, so carbon has 4 valence electrons, and so 4 vacancies, and therefore if you bond with 4 hydrogen atoms, each of them has 1 vacancy. And you can see this is methane, CH4. Okay, so CH4, and then so you have 1, 2, 3, 4, 5, 6, 7, 8, everything. So around the shell, so CH4, everything looks great from the atom perspective. So for every hydrogen atom, it has 2 electrons, and so therefore it's happy. The carbon has 8 electrons, and therefore it is happy. Okay. And that being happy means that you're stable and don't need to interact with things. Okay. And this is a molecule. Okay. Okay. Covalent bonds are when atoms share electrons. So here the electrons are shared. And the way we kind of think about it is like how strong atoms want electrons. Okay. Then that is something called electronegativity. Okay. So a electronegativity measures a atom's ability to attract electrons. Okay, so atoms with very low electronegativity doesn't really want electrons. Atoms with really high electronegativity really, really want electrons. So for example, oxygen really, really, really wants electrons. Okay. Na, sodium, okay, really doesn't want electrons. Okay. Okay. So this model that we're looking at, CH4, the carbon and hydrogen, they want electrons about the same. Okay, so this is about 2.6. This is about 2.2. So the difference is not very big. So they share electrons equally. Okay. Okay, and that forms non-polar covalent bonds. So they share equal. Okay. Some atoms have different electronegativity. So oxygen here is about 3.4. Hydrogen here is about 2.2. Okay, because one is much stronger than the other, oxygen will actually want the electrons more. Okay, so that is a polar covalent bond. Okay, so what will happen? We'll talk more about this in a couple of slides. But water, because the oxygen wants the electrons more, will pull the electrons more toward it. So this side will have more electrons, so there will be a slight negative charge. This side will lose the electrons, so it will be a slight positive charge. Okay. Okay. When there is a very, very big difference, okay, a difference of greater than 2, technically 1.9, but 2 is fine. The one atom can take the electron from the other one. So here, chloride has a charge of 3.3, or chlorine has a charge of 3.3. Sodium has a charge of 0.9. That's more than 2. So the chlorine will pull the electron off of sodium and completely and turn it into chloride. Okay, and you get this sodium chloride. Okay, so this is now happy because it is 8 electrons in an outermost shell. This is also happy because it only had 1 electron in its outermost shell, and to get rid of it, it now has 0, and it's happy with 8 electrons in the outermost shell again. Okay. Okay, so some atoms are partially charged, and this is water. Okay, like I said before, they have polar covalent bonds. Polar, when we talk about things that are polar, polar means that 2 sides are not equal to each other. Okay, so the oxygen has a slightly negative charge, the hydrogens have a slightly positive charge. Okay, and that's what the little delta sign means. Delta means partial, so delta negative, partially negative charge. Okay, hydrogen atoms, slightly positive charge. Okay. Okay. When we put these things together, okay, water molecules together, one side will be negative charge, one side will be positive charge, and that bond between them is a very weak bond, but very real bond, and that bond is called a hydrogen bond. Individual hydrogen bonds are really weak, but together they can generate huge forces. Because in water, there are millions and billions of these bonds working together. And hydrogen bonds is what makes water special. Okay, one of the things that we realize about life, and you'll see this in like every National Geographic PBS special that you watch about life, is that water is really important for life, and it is. And that's because these hydrogen bonds give water its emergent properties. Okay. So let's talk about the emergent properties of water. Okay. Water is cohesive. Okay. And that means water molecules stick to one another. Cohesion is the ability of water molecules to stick to another. Okay. And this generates something called surface tension. Okay, and you didn't try it when you want to. Put your hand in water, and as you pull it out, it seems for a split second that the water kind of sticks to, keeps your hand from breaking the surface of the water just for a little bit, and that feel is surface tension, and you can see that here as well. This little bug is actually heavier than the water, but because of surface tension, it can sit on top of the water. If I take this bug in, and I was really mean to it, I pushed it into the water, it would actually fall in and drown. But because it's on the surface, the water molecules want to stay together and push up, and therefore it's preventing the bug from falling in. Okay. Water is also adhesive. Okay, cohesion is ability to stick to each other. Adhesion is ability to stick to other things, and together, that's what makes water go up the tree. Okay. Okay, because water is charged, because water is polar, it loves other polar things, including ions and other polar solids. And because of that, we can dissolve things in water, like sugar and salt dissolve in water really well. Okay. So this is what happens when you add salt to the water. Okay, the water surrounds the salt, so you can see the negative charged things are surrounded by positive charged things. Okay, the positive charged things are surrounded by negative charged things. So they stay stable this way. So you can dissolve a lot of salt in water, as opposed to trying to dissolving salt in oil. You don't get very far. Okay. Okay. Because hydrogen bonds are stretchy, they allow stretch, and when they allow stretch, they absorb temperature. So it takes a lot of temperature. It takes a lot of heat to change the temperature of water. Okay, it's like you just think about it when you're cooking. If you have a pot, like you put the pot on the stove, the pot becomes very hot very quickly. But if you put water does not. It takes a while to heat up. It absorbs a lot of energy to heat this up. This is why the coastal regions have milder temperatures than the landlocked regions. Okay, I always use this example. LA compared to Las Vegas. LA, the temperature from day to night varies from about 10 degrees to 15 degrees. In Vegas, the temperature from day to night can vary 30, 40 degrees easily. And that's because we are next to the Pacific Ocean. During the day, the water absorbs a lot of the sun's heat, and that keeps the land cool. At night, it releases that heat and keeps the land warm. And therefore, the coastal regions, okay, don't have nearly as much temperature fluctuation as anywhere else. Okay. Okay. Also, because of hydrogen bonds forming unique structures in ice, when ice freezes, it becomes less dense than water, and therefore it floats on top of the water. And because ice floats on top of the water, ice can form a barrier to prevent sunlight from hitting the water underneath and warming it up. And it can also prevent the cooling effect, okay, the driving out of the heat. So it keeps the ice on top and water on the bottom. And that water on the bottom you can live under. So things can live under ice. And Antarctica and stuff like that. There's a lot of living things that live under the ice. All right. So water participates in chemical reactions, which we'll learn later. Okay. All right. And we'll stop right here and we'll go on to part 2 next time. Okay.